Today we shall have a very distinguished lecturer, Professor Enrico Sciubba. He is a professor for turbo machinery and energy systems at University of Rome, La Sapienza. His main field of interest is related to engineering thermodynamics applied to energy systems, particularly in turbo machinery, heat transfer. And in that perspective, we could say that we were very lucky that this week we had this opportunity. We would like to excuse ourselves because it was a very short notice, and we have invited you just in the weekend, and we were very grateful that you accepted this invitation. Professor Sciubba is also in a round trip here. He will be also in Bucharest at the University of Bucharest and Polytechnic University of Bucharest. So the subject for today, which was proposed, is related to a new approach, let's call it, in trying the engineers to solve the environmental problems. Because for many years it was always a sort of battle or a sort of debate between engineers trying to engineer the things which are not very natural and were harming the nature, and the environmentalists that they were considering that just by preserving the nature they are doing their job. And in that perspective, always when we are talking about a new plant or a new wind park or whatever, always there is such a debate. So from that perspective, we, the engineers in general, but you will see that Professor Sciubba with his team in Rome, he developed an approach based on exergy analysis and centering on resources to build up a, let's say, a possible approach for harmonizing, let's say, the constraints and interests. So, Professor Sciubba, please have the floor. So, also to our colleagues from Istanbul and Crimea, whenever you consider necessary, we shall stop and put the questions. Actually, I shall kindly ask Claudiu to send you by mail the presentation in PDF format to have it also in your site. So, okay, so we shall do, before starting, we shall do by Skype the transfer of the file in PDF format to have it also on your computer. Okay? So, poți să faci treaba asta de pe display-ul ăla și să lași display-ul? Okay, so, Professor Sciubba.
Thank you very much for the invitation and for the nice words. And well, bună ziua. I don't speak Romanian, unfortunately. I don't speak Turkish nor Russian, so I have to speak English. Good afternoon in EDU, Professor Iavuț, and good afternoon in what is it, Chișinău? Professor Bulgaria.
Hello, Claudia.
Hello.
Excuse me, Claudia, do you hear us?
I hear you.
You not hear this microphone? Claudia.
Can you speak closer to the microphone?
Okay. Do you hear me now?
Hello.
Do you hear me? Hello? Do you hear me? Hello? Do you hear me? Professor Iavuț, Professor Mazinov, do you hear me?
Just one second.
Zeynep Hanım, duyuyor musunuz? Size bir ricamız var. Çünkü orada sizin mikrofonunuz çalışıyor. Siz mute yapın. Çünkü orada kendinizin aranızda konuştuğunuz burada da duyuluyor. Olur mu? Sağ olun. Sağ olun.
Okay, we are all set. You hear me? Yes? Okay, so I'll start. Thank you again and welcome to this lecture. This is, what I'm going to present is a shortened version of the PDF file. Because the PDF file contains something like 130 slides and that would kill you, and I decided to shorten it. In spite of this, there are more than 80 slides, and I ask for your forgiveness, but I will skip some slides because we want to keep the time into check. As Professor Mahmoud told you, I'm a mechanical engineer interested in design of energy systems and especially of turbomachinery related energy systems. Now, my interest in the environment was originated by exactly the remarks that Professor Mahmoud made. There's been a conflict for many years between energy engineers who build plants and environmentalists and some part of the politicians who keep saying that we are polluting the world. But they don't want to renounce their cars, their free electricity, their electronic gadgets and so on. So my interest was to show that, of course, as engineers, and especially as system engineers, we design and we can design systems that abide to environmental regulations at a cost. And the cost, this is the novelty of the approach which I will present at the end of this presentation. The cost is computed not in monetary terms, in my formulation, but in resources. So we will not be talking about money, we will be talking about resource consumption, because that's a real harm to the environment. To do this, I will structure my presentation into two parts. First of all, I will talk about environmental indicators. And then I will briefly discuss the merits of some of the environmental indicators which are most popular today. I will show their strengths and weaknesses. I will try to convince you of the strengths and weaknesses. And then I will explain my new method, extended exergy. Okay, that's the plan of the lecture. I have left with Professor Mahmoud both the slides and the PDF of the presentation. So you will have the material if you need to look at it. My email address is on the slides and on the presentation. If you need to contact me, you write or you contact Professor Mahmoud and he will contact me and I will try to answer your questions, okay, if I can. Okay, let's start. We are talking about, first of all, very large and complex systems. We are talking about power plants, we are talking about sectors, industrial sector, transportation sector, extraction sector in a society, very complex things. And to study these complex things, what is illustrated in this first slide, slide number 2, is the Italian system, which is composed of extraction, conversion, agriculture, industry, transportation, tertiary system, and domestic system. And all the systems are interconnected. And all of them are connected to the environment. And to this small part is Italy, is the rest of Italy. So every complex system has a counterpart in the environment. So we cannot exist without interacting with the environment. That's the main thing. Complex systems are simpler complex systems like a gas turbine or more complex systems like this. We have a common characteristic in the systems: internal connections and external connections. And we have to study these systems by considering them as thermodynamic systems. This is the basis of my approach. Okay? They are uncommon, let's say, thermodynamic systems. They are extended systems because we include some features which are not only dealing with the technical stuff we study at the university, mass flow rates or temperatures or enthalpies. There is also some environmental flow, some exchange of flows from the environment into the environment. And I will try to convince you that the study of the transformations can be used to describe the rate of exploitation of natural resources. Because I'm only worried here about the interaction between a system and the environment. There is a meta-paradigm, a way to treat this problem today, which consists in the following. There is a bunch of scientists, environmental scientists, engineers, physicists, chemists, biologists, and unfortunately economists and sociologists that define some indicators that we call environmental indicators or ecological indicators. I will refer to them as EI in the following. Then these indicators are used by national or international agencies to evaluate plants or systems. And there is a clear necessity to make the communication, to improve the communication between these two groups. Because a policy decision maker is not always, and usually never, versed in engineering or environmental sciences. So he needs an environmental indicator which he can trust. It has to be simple and useful. So the indicator has to transmit both quantitative and qualitative information. And this is not an easy task. It has to provide some numbers, but also numbers in a correct way, from good to bad, or worse, or better, or things like that. And that's not easy. And I will try to show that some of the most commonly used environmental indicators lack the necessary sharpness. So what I do, I first describe some indicators and do a critical analysis, and then present my view of the problem. What is, first of all, why do we use an environmental indicator? What is an environmental indicator? What are its properties? What are its goals? This is what we're going to discuss next. This is a definition which I insist with my students that they memorize. An environmental indicator is an aggregate, every word is important here, quantitative measure of the history of the relevant impact of a community on the surrounding environment. Every word is important. It must be applied, an environmental indicator, ecological indicator, the two words are synonyms, to every community. To a community of nomadic hunters in the North Pole, to a large city, to an industrial plant, to whatever, to a spaceship. An environmental indicator is aggregate. It doesn't make sense to speak of the environmental impact of one person, single person on the environment. There is none. It doesn't make sense. You have to talk about communities, a group of people which I will refer to as a society or a community. And the environmental indicator must assess the relevant impact on the environment of this community in space and time. That is, it's linked necessarily with a history in time, and it's linked to a concept of surrounding environment. In the other slides that I'm not showing, I make this important point. Some environmentalists insist, you have probably read this somewhere, that the flapping of the wings of a butterfly in Brazil influences the climate in Australia, to show that the world is one living planet. This is true, but for our scope is irrelevant. When we talk about the environment, we always need to define the environment in a very much more restricted sense. So we have to define the space region, the spatial region, to which we apply our environmental indicator. This is very important, otherwise the environmental indicator will lose completely its meaning. So, I'll give you an example of what is not an environmental indicator according to that definition. The gross national product, which is very often used. You see that on TV, politicians talk about it, you read it everywhere. It's not a proper environmental indicator because it doesn't give you a real measure of environmental impact. The CO2 atmospheric concentration, it's not a proper environmental indicator because it doesn't separate the anthropic sources made by humans from the natural sources. And that's been a big debate about A volcano eruption brings about in the atmosphere 10,000 times the CO2 that we bring about in one of our societies. So we have to separate the natural and the non-natural effects, the anthropic effects. Life standards indicators, like the standards of life, the human, the health, the health index, they are not proper indicators because they are based on the standards of education, length of life, schooling, alphabetism, and these kind of things that's not related directly with environmental considerations. Social equity indicators, they are not proper environmental indicators because they are based also on a different paradigm. So, if these are not indicators, how do we build an indicator? What are the properties? Well, it must be expressed, first of all, we are engineers, by a number, a numerical expression, which goes from bad to good, from 0 to 10, from 0 to 100, some number that we can rank. Okay? Second thing, must be calculated on the basis of properties of the community and of the environment. Both of them, not only one. It must be normalized. It's useful to have indicators which are ranked from 1 to 100 or from 1 to 10. Not to have things like 2,532 or 2 millions and something like that. That's not useful. It's useful if you can rank the indicators on a normalized scale. 0 to 10, A to Z, something like that. It must be calculated using a method which can be reproduced by anybody. So if I propose a method today, which I will, it must be calculated, the same method should give the same result if calculated in China or in Mongolia or in South America. This is important and it's not always true of the indicators which I'm going to discuss later. And it must comply, very important, with the accepted laws of physics. In particular, we know mass conservation, energy conservation, and entropy generation. These are, continuity, first law, second law. And I will be showing you that most indicators do not comply with second law, and which is really the reason for proposing this new method. We have to be careful when after we build an indicator, we have to be careful on how we use it. So the only proper use of an indicator is to measure the impact of the community, society, sector on the environment. It cannot be used to establish value rankings. Of course it's good if the employment rate is 100%, but you cannot build an environmental indicator on this. It's not relevant. It has to be built on properties which put into play the system and the environment. It should not be used to provide ethical issues or social issues. This is a big danger. Many of these indicators have been used to say that one form of government is better than another form of government or anything. These are political issues or ethical or social issues with nothing to do with environmental indicators. So we have to be careful because we often read in the press and also in specific books and in journals that you want to use these indicators to provide guidance in ethical issues or something like that. That's not the case. The only use is to assess a system, a societal sector, a process or whatever, either by itself or in a comparative basis. This is what we call examining alternative scenarios. So suppose we want to bring electricity to faraway places. We have two choices. We build an electric line from a central station, or we build a small engine on that place, which is a very important issue, for instance, in Africa or places where sparse populations live. Well, we can compare the two alternative scenarios and decide which one is better for the environment, in the sense that it produces the same effect on the society, same kilowatts installed, without or with the least environmental impact. This is the scope of an environmental indicator. Now, let's see which indicators are used currently. The first one, it's called the first one of my list. There are many. I'm talking only about global indicators which have been well published and well researched in the past. There are thousands of environmental indicators. I give you an example. There are indicators, biological indicators, that count the number of bugs living on a hectare of land in a certain place. Of course, that is important for the bugs to begin with, and also important for the birds who feed on the bugs, for the foxes who feed on the birds, and so on and so on. And it's not important for our purposes. Okay? This is a local indicator. I cannot say there are so and so many bugs in Siberia. That doesn't count. I want to study an impact of, let's say, a relevant impact. So I cannot deal with local indicators. I will only deal with global indicators. The first global indicator was proposed in the 70s by a group of World Bank economists. And it's called material throughput analysis. What was the idea? It was brought forth in the US. The idea was to counter the concept that was being applied in the 70s, especially in the US and in all the industrial world, that expansion of an economy was good for the benefit of the society. These guys said it's not correct to say so, because if we count, we can express the lifestyle of a society, of a community, in a global equivalent material flow, we can show that the capital of material, the amount of materials which are available on Earth, will be decreased constantly. And the more the economy grows, in this sense, the more materials we use, the worse it is for the environment. Remember, these are in the 70s, and many of you were not born. I think only 2 or 3 were born in the 70s and were grown up enough to understand this case. But this was a change of attitude which was bitterly fought by politicians, by industry. These guys had a terrible time. Okay? Very difficult to put on this concept. The idea was, what came out of here is obviously recycle, which today seems natural to us. In the 70s, there was no recycle. I think Professor Mahmoud can vouch for this. We didn't care about recycle. So when we had some plastic, we threw it away. Copper, we used it, we threw it away. Metals, scrap metals. So there were huge depositories of scrap metals. Cars, especially in the States. Okay? These guys started saying it's not good if you use too much of the earth minerals. And they did that in this way. They considered, well, this is my rendition of their method, the society and the biosphere, and made a very simple mass integrated, so time and space integrated, mass balance. The society extracts from the biosphere primary resources, material resources. They go into the society uses them, consumes them, accumulates them, builds houses, for instance, or cars or whatever, and then discharges some of these into the biosphere. Of course, the society accumulates, so the balance is not zero. If you take 100 from here, you will discharge maybe 40%. So the rest is accumulated in the society. But you still deprive the biosphere of 100. Okay? This is the basic idea of mass throughput analysis, MTA. And the environmental indicator is a normalized mass flow rate of resources, like kilograms per person per day or per year of some material. Is this clear? Okay. Now, there is an accounting system, of course, and this is the balance. The mass, the sum of all the masses going in minus the sum of all the masses discharged is equal to the mass accumulated in the society. The index I here, and J and K, account for the materials. Okay? because, of course, material J, iron, is extracted from the earth, but the discharge is not iron, it's steel, for instance. Okay? And the accumulation, it's not in the form of iron either, it's products. So the indexes here, J, K, and I, are different. I don't know if this is clear enough, okay? So they claim that this is based on the laws of thermodynamics. Well, I like MTA because it's a good starting point, but this statement is not true. It's based on a mass conservation through a proper system of an input-output Leontief type accounting, but it's nothing about energy there. Nothing. There's nothing about toxicity. There's nothing about entropy. Only conservation of mass. So, well, I will give you the way you account for it. You take the basic materials and you see how many of these materials go into the manufactured materials. For instance, you need minerals, I don't know, rubber and water to build iron and steel. And then you see how much iron and steel goes in buildings, roads, electrical equipment, and so on and so on. So, and then you measure backwards how much steel we have in a piece of furniture, the desk. You know because you have run this balance. And then you know how much water, rubber, wood, minerals, and so on went into that steel. So you can measure how many kilograms of basic material you had to extract from the earth to build one single bench. Then you of course say, okay, 40 people use this bench, then you divide it by 40, and that's the use of material per person per year. Okay? This is in principle the balance. If you have questions, ask. So, there is a point about fossil energy, because in a mass account, you cannot account for fossil energy. Fossil energy is accounted for in barrels of oil, tons of coal, and so on. Material. Okay? So the energy is accounted for on a material basis. And the question is, how do you account for wind? How do you account for tides? How do you account for hydraulic energy? How do you account for solar energy? They were not concerned with these issues because these had been proposed in the 70s. Okay? These issues were not big at the time. The idea, though, is to account for fossil energy on a basis of material balance. So, well, okay, we'll skip that. Strengths. MTA provides a direct quantitative measure of the actual material energy, tons per person per year. So this is one of the definitions of an environmental indicator. It's good. It quantifies the link between the human activities and environmental analysis. If there are two societies, one of which is using 10 tons of iron per person per year, and the other one 5 tons of iron per person per year, the second one, of course, from this point of view, is more environmental friendly than the first one. So it's a very easy way of comparing use of materials. And it can be used for planning, management of material, okay? And to also to monitor the implementation of different scenarios. This can be very useful. And also it can detect what is called the problem shifting. That means we import in the West, we call ourselves the West, okay? We import many basic materials from regions of the world which we call the South, I don't know why, but pre-industrialized countries. Africa mainly, Southeast Asia, and South America. So we use the materials, but we take the materials from the environment of those countries. So we are using their material for our purposes. This is called problem shifting. Of course we pay them, but MTA is not concerned with money. It's concerned with resources. So if we extract some diamonds or gold in Africa, it doesn't matter that we pay them with cash. The fact is, we are mining materials from Africa to use them here. So we say we are not polluting here. Hey, we don't have gold mines here, but maybe in Romania we do. But let's say aluminum mines. But we do use their aluminum. So we are shifting the environmental problem to them. This was a big issue in the 70s. Now, I see many of you laugh because this is normal for us to consider this. But 40 years ago, it wasn't, believe me. Okay? I was even born 40 years ago, of course, but I know that. I was born, unfortunately. And it can be applied. I was already married, I think, 40 years ago. Yes, I was. But I got divorced very soon, so no problem. I got married again then. I also divorced very soon, and did it 3 times. So it can be applied to different levels of aggregation. It can be applied to a plant, it consumes so and so many tons of iron. To a city, it consumes so and so much iron, plus some cement, plus some natural gas and so on. It can be applied to a society. So it allows you to use different size for the systems you are studying. It's a good thing. And it is based also in the 70s, that was a new thing, on a life cycle bookkeeping method. Now, every kid in school knows what life cycle means. In the 70s, we thought the life cycle was the span of human life. These guys were the first to integrate the results in time. So the mass balance that I showed you before, the equation, was integrated in time. And that was a novelty. And that's important, because resources are not infinite, so the integral in time of our extraction is the diminishing of the natural capital of that resource. So this is a very important point. And it places emphasis not on the financial efficiency, not on capital, but on materials, natural resources. Saying that, there are limitations. Several applications are not standardized. They use different methods. If you remember, I told you that you have to use a single method that everybody can reproduce. The several applications which have been published for MTA, they are not standardized. Toxicity, second weakness, is not proportional to mass flow rates. Suppose we have 2 societies, one of which discharges 1 ton of arsenic in a river, and the other one half a ton. We would say that the second society is less polluting than the first one. But if the first one also discharges 10,000 tons of iron products in the environment, and the second one 30,000 tons, it's not clear which one is more polluting. So, and the reason is that toxicity is not proportional to the quantity of material that you discharge in the environment, but it's proportional to different things, which we will discuss later. The harm of that material on the environment, which we have to discuss. What we really mean is the damage to us. We will discuss that later. But this is the weakness of material throughput. Energy flows, as I said, are only indirectly accounted for. Solar and wind energies are not treated. And where is entropy here? We didn't talk about entropy. There is nothing about entropy included in an MTA analysis. So, well, this is an example I was talking about before, but let's concentrate on this. About the 5 principles that I said that are important for the analysis of an environmental indicator, the green ones are the ones which are okay. So MTA is good for a measurable numerical expression, and it's normalized. But the yellow are the ones which are it's not really reproducible, because there are different methods published. And it doesn't comply with all the laws of physics, only with mass conservation. Not with energy, first law, not with entropy, second law. And it's not based on intrinsic properties of both systems. Why? Because of toxicity. Toxicity is not an intrinsic property of the environment. Toxicity is related to us, not to the environment. We die. The fish we eat dies, not the environment. The environment survives, changes state, as we will see, but survives. So it has 2 good points out of 5, 2 average points out of 5, and 1 red point, which makes us not like it. The second material-based method is very popular today. I'm sure you have read it in the newspapers. If you go on the internet and type ecological footprint, you'll find whatever results you want. It's basically a material accounting, which was proposed much later, in 1996. And that's a very smart way of proposing it. It's the amount of land and water that an individual person needs to cover all of his needs. Okay? We need some wood, we need some iron, we need some concrete, we need some electricity. Where do we take these things from? From the environment. How much land do we need to make 1 square meter of wood? So and so much land. How much water do we need? So and so much water. And how much food? So and so on. And for the energies, you take the solar energy per hectare, or wind energy per hectare, and so on and so on. So it is basically a material accounting. So what is the balance that they strike? You have a society. This society interacts with a portion of the environment, and this portion of the environment which is needed to feed completely this society is called the environmental footprint, which is the amount of hectares that this society needs to survive at its present standards. Okay? Very smart method. And it also has a very important results that we are living, I'm sure you read it, we are living on 1.5 planets. That means we are consuming resources at a rate which is higher than the rate that our Earth can provide. And sooner or later we'll go to a catastrophic state in which we will be short of resources, material resources. This is what material resources in the sense of land, arable land, that can produce fruit, can produce fish, the water, can produce animals, can produce food and materials for us. It's very, very popular now. I'll skip this, you have it in your, this is the definition. This is very popular now because it can be applied to country level and show that there are countries which are living, which have an environmental footprint larger than their surface. I think Romania is one of those. All Europe is one of those. And countries like Australia, Mongolia, Gabon, and other countries, which are living below their, in other words, the size of the country produces more stuff than needed by them to survive. Of course, we are using it. So, environmental footprint gives you this measure. The largest environmental footprint in the world is today in the United States. China is growing very fast, India is growing very fast, and the environmental footprint analysis shows that there are limits to their rate of growth, to their feasible, environmentally feasible rate of growth. So this is an important result. Well, this is, and you find these results like you can compare different technologies. What is the footprint of wind turbines? Well, that's a mistake of environmental footprint. 0. It's not true. You need steel to build wind turbines. You need plastic. You need a lot of material. You need work. I mean, people working on it, and people eat and live and consume environmental resources. So this is a limitation. But clearly, they can be used to assess the way you produce thermal energy, for instance, using biofuel, or fuel and wood, or fossil fuel, and so on and so on. So that gives you useful information. Remember, one of the features of environmental indicator is to compare different technologies. And environmental footprint is good for this, in comparing. This is very famous also, the map of the world, not to scale, where every country is represented with, not with its real kilometer squares, but with its environmental footprint. And this shows clearly that there are areas in the world where the environmental footprint is low. This is, I don't remember which year, but it was some years ago. China is still rather small, and India is still rather small. Now they've grown too. But look here. Okay? The countries which are publishing more papers on environmental footprint are those who have the highest environmental footprint.
Look also to South Korea and Japan.
Yes, yes. Look at Japan. Look at Japan. Japan is bigger than Africa. Okay? That means that they are consuming a lot of material resources. And that's true, compared to other lifestyles. So this is a good way of comparing these things. These maps you find in internet, and they are published in schools, you know, to give young guys an idea of what environmental concern means. The strength. The methodology is a detailed input-output analysis. It's like MTA. The accent is on renewable resources, and that's important because the new concept of environmental footprint is that it doesn't care too much for fossils. Of course, it gives you a measure of fossil consumption, but the main thing is how much solar energy falls on Earth. That's renewable. How much wind per hectare can we gather wind energy? How much hydraulic energy per hectare is available, tidal energy, and so on and so on. This is renewable resources. And the good thing is that they shift the accent on renewable resources, because if we are talking about sustainability, which I think it's wrong, we will never be a sustainable society in the present standards, we cannot survive on fossils. Fossils are finite. So we have to find a way to survive forever on renewables. That's the important thing. And environmental footprint is very good at this. Gives you a measure of renewables. It's also good because they're always explicit in their assumptions. It's very well formulated. Backernagel is a Swiss guy. So you read his papers, it's like reading a Bible. It's very precise and very clear. And also they have, both of them, Ries and Backernagel, have a very positive approach. If you have a critique, you go on the site and post a critique, and they do answer. And they will, of course, out of 100 critical remarks that are published there, 99 are bullshit. But the one which is good, they answer, and there have been cases in which they modify their theory to account for the criticism. This is a very scientific attitude, which is not very common in other people, including myself, of course. I don't like being criticized. And environmental footprint can be used comparatively. Well, why? No, okay. It's good, it's good, it's good, it's good. What are the limitations? That it neglects, again, toxicity. Because it's a mass accounting. Okay? How much ocean surface do we need to catch the fish we eat? Fine. But how much ocean surface do we need to dispose of the pollutants that we put in the ocean? That is not accounted for. But it's accounted for, but not on toxicity effects. So it doesn't account for mercury in the seals or polar bears or stuff like that, fish, tuna-fish, things like that. It doesn't account for that. It accounts for the mercury, but not for the toxicity. So that's a weakness. And it provides limited information about non-renewable stuff, because it focuses on renewable. And of course, it has this concept of hectares of useful land, but it uses average values. And the hectares of land in Siberia are not as productive as the hectares of land in Romania, around Constanta. So that would have to be taken into account too. They do it with corrective measures, but it's not easy to do that. So this is a problem which is called the local impact problem. Because an hectare in Constanta, of course, produces more stuff than an hectare in Siberia or in Antarctica. And that is a local problem, not a global problem. Of course, if you want to import stuff to Antarctica, then you have to increase the environmental footprint somewhere else. But still, you are exporting the problem from Antarctica to other lands. So this is not taken well into account. And it has also a problem which is called the subscale problem, but this is really a small problem, which has a few types of productive land, like cropland, forests, open ocean, lakes, and stuff like that. And there are more differentiation in places. Like there are rivers that produce a lot, rivers that produce little. So this is called the subscale problem, and that has to be solved on a local basis. So it detracts of the generality of the approach. So what are the strengths? It's measured numerical expression, it's green, okay, but it's yellow on the intrinsic properties of both systems because of toxicity. Normalized, it's difficult to normalize it because of subscale problems and local versus global problems, and laws of physics. Where is second law? Where is first law? Only a part of first law is included, but second law is completely absent. So, before we proceed, I have to explain why material-based methods are not good for building environmental indicators, or why I think that they are not good. This is the Earth. The Earth gets a solar radiation of so and so many terawatts per year, takes some cosmic radiation which has not yet been measured completely, we don't know how to measure it, neutrinos, photinos, this kind of stuff, and re-radiates a lot into space. So we live on the difference. Life on Earth is maintained by the difference between this plus this minus this. We will only consider 173,500 less 171,600, so about 2,000 something terawatts per year. The Earth is a closed system for material. The last time a substantial amount of material was lost by Earth was when the moon was formed. And I wasn't born at that time. The last time we had some materials added substantially to the Earth was on the meteoritic impact that caused the extinction of dinosaurs. That's the theory. A big meteorite stroke
Yucatan.
Central America, Yucatan. And the clouds lowered the temperature of the Earth so that the reptiles became extinct 65 million years ago. Ever since, there has been no material addition to the Earth. Okay? I mean, it's been negligible. Some meteorites fall now and then, they're kilograms. Okay? So, from the thermodynamic point of view, it's a closed system for material exchanges. We don't get anything out, except the satellites. We don't get anything in. From the context of energy exchange, it's an open system, because it gets energy and re-radiates energy. So, the real thing is to consider what was called the spaceship concept analogy, which was, you recognize this picture? You know
Battlestar Galactica.
Ah, you didn't know. You never watched Star Galactica. You have to. It's an instructive series, Star Galactica. Well, it's also dated. The analogy was made by Kenneth Boulding, who was a professor of mechanical engineering at Colorado State in 1966. But still today, very few people know it. That's why I'm always making this point in my lectures. And the analogy is this. Da, 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 da. You remember this? This you've seen the movie. Imagine, Boulding said, imagine that we send a large fleet of spaceships into space. Okay, I made this to show my culture, we send it to a galaxy with 25,000 light years from Earth. And we have 50,000 people. They have to survive for 25,000 years. Of course, they will individually die, so they have to be sustainable for 25,000 years. How can this be made possible? Well, they are a closed system from a material point of view, because they can't get matter from space, but they are an open system from the point of view of energy. So they must recycle, and they must use the energy to renew their materials. Okay? They destroy some copper, they use the energy from the sun or the stars to melt the copper and recycle it. Well, the analogy is very clear. We are space. We are Battlestar Galactica. We are spaceship Earth. So the idea is we cannot fund our sustainability considerations on material because we are a closed system. Sooner or later, we will die out. We will run out of material. It's very simple. And maybe it will be 5,000 years, fine. 10,000 years, fine. 1 million years, fine. But we will end our supply of materials. So we have to deal with energy considerations.
Could we have a break now?
Sure.
Is the appropriate time?
Let me see the next slide. The implications are clear. Okay, let me finish this and then we can start. A proper environmental indicator must be based on energy and not on mass accounting. So that's why NTA, an environmental footprint, and all other techniques based on mass balances are, well, I don't like them to build environmental indicators. Okay?
So, we shall have now a break because this was the first part of the presentation. While he didn't build anything, he just destroyed. So, Professor Mazinov, do you have any question?
Thank you. Very interesting lecture and very high field of science question. 1 minute, I must my voice.
So we shall have a break of 10 minutes. But if you have now a question regarding to the aspects that have been presented, like the criticism of the two indicators, you can raise them now.
Oh, in my point of view, I think about this. Some of important part of analysis is energy, law of energy, safe energy, and I think that mass analysis and mass saving law important too. But I think that, in my point of view, that energy law, safe law, energy maybe more sensitive and more important. I think. Sorry if I am.
Yeah. Thank you very much. So, in principle, you say that you agree with these limitations of the mass analysis. Now, let's move to Istanbul. So, the group in Istanbul, the ladies there, do you have any question or comments up to now? Hiçbir sorunuz falan var mı?
Şu an yok hocam, teşekkürler.
Tamam. Okay, so we shall have now 10 minutes break and we shall come back in 10 minutes. So, de aici din sală dacă au întrebări.
No questions.
Domnul Joachim.
Well, I can't say that I have not any question because, in my opinion, of course, it was really interesting and, of course,
You agree with this point?
I hope that most of us know, at least in part, know the ideas which have been presented.
Thank you very much. So let's make the break and then we'll come back with the refreshed.